Hi guys, day 2 of circles. I'm hoping you're thinking these are easy, and they are. Today's lesson is just as easy, but we will learn some new things maybe you've not heard of before. So let's look at our vocabulary and our I can statement. So we're going to use chords of circles, so we need to learn what those are to solve for missing links. So on the next pictures that you'll need to see what those look like. Alright, so chords are segments whose endpoints lie on the outside of the circle. So as long as you have a point on the circle, a point on the circle, and connect two of those, you have a chord. So common chords would be ones you know already. Not a radius. Actually, a radius is not a chord. Sorry, that's in there. But a diameter is a chord. So for instance, if this is point A and this is point B, then AB is a diameter because it goes through the center, and it's a chord because its two endpoints are on the circle, on the circumference of the circle. All right, other ones. This is a chord from C to D and a chord from E to F. If we just label those endpoints. And a chord is simply a line segment. So you do name it something like this. You still write it with the line segment notation there. Now, this next picture is one of the cool things about chords. Congruent chords, and those are marked with these lines right here. That means those two chords are the same. They will form congruent central angles, which means when you draw in the triangle or connect from one endpoint to the center to the other endpoint, and you've got this angle going on, then that angle would be the same as this angle since those chords were the same. So it's kind of like what looks true is true, but you got to be careful about that. Another important piece of information here would be something to remember because you'll use it a lot. Anywhere you have a radius, all the radiuses or radii, all radii, oops. So once you see, for instance, I know I'm already drawing all over it, but from here to here is a radius. Well, this is also a radius, this is also a radius, this is also a radius. Now, even those chords on this particular picture look the same, that's not necessarily the case. That just looks true in this one. So let's see what we can do. Example 1 is almost so easy, you're going to go, well, I'm not even using chords really. So let's solve for x, and in the picture, x is this length. The first thing I want you to do is think radius. That's what we were just talking about a while ago. X is a radius. Here's another radius. Here's another radius. There's several on here, but here's the one that matters. Another radius is 14, so x is 14. Let's look at the second picture. Let's find all those radiuses, radii first. Here's a 6, that's a radius. So that would be a 6, which is labeled. That would be a 6. Here's another 6. So we just found what we were looking for. But let's go ahead and do a second part of this problem, which is going to come up on the next page. Could you find me this length right here? Let's call that y. Yes, you could, because look at this entire length. From here to here is yet another radius. So 6 minus 3.9 would give you that y length. Y should be 2.1. So you'll have to do that on the next problem. So let's keep going. Example 2. Now the pictures get messier, but again, think radius lengths and think chords. And then I'll show you one other neat trick coming up in a couple more examples that also is always true with chords. 38.8, that represents this entire length. And what is that? That's a diameter. So if a diameter is 38.8, since we know we're after radiuses probably, and let's look, x is this little part, but that is part of that whole length that I've shown right there, which is a radius. So if we can just find a radius length, we're good. So if the diameter is 38.8, the radius will be half of that. That should be 19.4. So 19.4 is not our answer for x, but 19.4 is our answer for r. So now if we'll go 19.4, think about what you need to subtract to find x. You need to subtract the other section of that radius that we were given. Subtract the 10.9. Your answer for x should be 8.5. Let's look at the second picture. X is just a section of a whole radius here. So here's a radius, and we need to find just the one section of it, this X. The 7.5 does belong to this little section, and 16 we're going to assume belongs right here. I'll tell you about that in a minute. So once again, let's find a radius length. 20.9 is listed right here and right here. So since they didn't list it as they did in the other picture in the middle, that means that's half of that distance. So a radius length is 20.9. We need our little blue section, which is a radius. So 20.9, and X is part of that. So 20.9 minus the 7.5 that they gave us, and X should be 13.4. Now, let's just make another quick note here. Do you see that 16? This is always true of chords which are intersected by a radius at a right angle. That was a mouthful. Listen to that again. Take any chord, for instance, I'm going to label this one AB, intersect it with a radius that hits it at a right angle, that right angle mark right there, and it will always split it in half. So if 16 is on this side, 16 is on that side. That'll come in handy in a few minutes. Pirates. I know you get it. Okay, let's look at example 3. Example 3 is just reminding us of the Pythagorean theorem because we are going to use that here in just a few minutes. You've already kind of seen where those right triangles show up on circles. I'm just going to write down how you set these up, but I hope you could recognize either one of these. This would be a leg squared plus a leg squared equals the hypotenuse squared. Do that work and you should get that X is 10. I hope maybe you didn't even have to do that. If your teachers told you about 3, 4, 5 triangles, and then if you remembered that 6, 8, 10 happens to be a multiple of 3, 4, 5, you could have figured out the 10 without having to do the math. All right, on this side, leg squared plus leg squared equals hypotenuse squared. Do that work, X should turn out to be 5. And again, some of you may remember we talked about special right triangles. 5, 12, 13 is a special right triangle, and you could have known that one without doing the work. We need to use that Pythagorean theorem a lot on chords and radiuses and circles. Like right here in example 4. So we need to find this X value, and the first thing you need to recognize is that this is a chord, we'll call it AB, that's been intersected at a right angle by a radius. So when that happens, that chord gets split in half. So if this is X, this section over here is also X. Once we have that, all we need to really now focus on is that triangle sitting right here, which is a right triangle. We need to find X. We have a 10.6 and we have a 21.3. Let's set up the Pythagorean theorem. A leg plus a leg squared equals 21.3 squared. You do the work. I'll pause it just a second, or you should pause it just a second and see if your work matches mine. Don't forget, when it is one of your legs missing and you have the hypotenuse, you set the Pythagorean theorem up like this with the missing value on the left side, and you'll subtract to get that 341.33. Value for X is 18.5. So once we found this X on this triangle to be 18.5, then this X is also 18.5. We are done. Okay, that's it. It is that easy, but it can also be that tricky because your eyes may overlook a radius or something in the circle. So you really want to pay close attention, and as always, the more you do, the better you are at it. So please do your assignment today and finish it up tonight if you need to, so that you're not getting behind. There's more to learn next time about chords.